Some of you have asked me to do question 7 on the practice exam. This is a good review of rotational kinematics. So let's start with the problem. Here's how it goes. A machinist turns on a grinding wheel and does so at time t equals 0, and the initial angular velocity is just 0. And then what happens is the wheel accelerates uniformly from rest for 10 seconds. So now t equals 10 seconds. And here's the wheel, and it's rotating. And now it's got an angular velocity of 96 radians per second. Now, the wheel is run at that angular velocity for 40 seconds. So it goes 40 seconds later. So now it's at 50 seconds. T equals 50 seconds. And then what happens is the power is shut off. And eventually slows all the way down to basically have a final velocity, an angular velocity of 0. We don't know how much longer it takes, and that's the question. So it's just going to slow down from this situation here where it's rotating to something like this. We are told, though, that when it does slow down during that process, it has an angular acceleration of 1.5 radians per second squared. Remember, accelerations are always per second squared. So we want to find the time. So that's the thing that we're after here, the time it takes to slow down. And we would presume that as it runs during this time, it still has an angular velocity of 96 radians per second because it was running this way for 40 seconds. So it was just left on and it just kept going around and around and around like that. And then the power is shut off and then it decays in its velocity. So how are we going to solve this? This is one of those angular kinematics problems, and let me just write down the different kinematic equations here. And the basic idea is that instead of having v, we're going to have angular velocity omega. Instead of having acceleration a, we're going to have angular acceleration alpha, and instead of something like a delta x, we're going to have some change in angular position. So these are the different things we're looking for to make substitutions based on our previous knowledge of the kinematic equations. So for this particular problem, what we can see is we're after the time. We want to know what that time is. And I think we've got the initial angular velocity here. So let me just sort of circle this. This is the initial angular velocity, and this is the final angular velocity. And we know alpha, and we want to get the time. So I think that leads to this equation here. So let me write that stuff down. The final angular velocity is 0. The initial angular velocity is 96 radians per second, like that. And then the acceleration is 1.5 radians per second squared. And then that's all multiplied by t. You just separate this. And we want to solve for t. So I get something like this. 96 rads per second equals 1.5 rads per second squared, like this, times t. So t is going to equal 96 radians per second divided by 1.5 radians per second squared. And if I plug in 96 and divide it by 1.5, I get 64. And seconds cancels with a second, so now I have a second downstairs, but because I'm dividing by it on the denominator, it's actually like coming up top. So it ends up being 64 seconds is the answer. The time it takes for the grinding wheel to slow down from 96 radians per second all the way to 0 radians per second. So given that we know the angular acceleration. So I hope this was helpful. It's just an example of how to apply the kinematic equations in rotational space.